Welcome to another episode of Tuesday Trivia. This is Kumar Singh, and the question that we are going to or the topic that we are going to discuss today is what exactly is parallelism, or specifically multi-GPU training. So we know that massive parallelism is one of the key advantages of GPUs, right? And it has led it to ride the AI wave, right, of massive data and massive computations. And it's the parallelism that basically helps address those complexities of massive data and massive computations, right? Now, when we talk specifically from the lens of AI model training, a key term that you may come across is multi-GPU training. So the trivia question that we are going to discuss is what are the different approaches of multi-GPU training. So multi-GPU training paradigms can be categorized into two specific groups, right? So you divide data for parallel processing with multiple GPUs and divide the model among multiple GPUs to handle memory constraints when the model size surpasses that of a single GPU. So data parallelism falls into the first category, right? Whereas model parallelism and tensor parallelism, and we are going to discuss them, cover them shortly and briefly, fall in the second category, right? Then we have techniques like pipeline parallelism that borrows idea from both categories, right? In addition, many current software implementations and others, they actually blend multiple approaches into a hybrid technique rather than using exclusively one approach, right? One thing that we have to remember here, that we are using the term GPUs to describe the hardware utilized for parallel processing, right? However, the same concepts and techniques discussed can be applied to other specialized hardware devices also, right? Such as tensor processing units, TPUs, right? Or other accelerators, depending on the specific architecture and requirements of the system. So let's get started with model parallelism, right? Or inter-op parallelism. Well, it's a technique in which different sections of a large model are placed on different GPUs and are computed sequentially with intermediate results passed between the devices. As you can imagine, this allows for the training and execution of models that might not fit entirely on a single device, but it can require intricate coordination to manage the dependencies between different parts of the model. Model parallelism is, I think, in my opinion, it's the most intuitive form of parallelization across devices, right? So for example, for a simpler neural network that consists of only two layers, right? Layers and an output layer, we can keep one layer on one GPU and the other layer on another GPU, right? I mean, of course, this can scale to an arbitrary number of layers and GPUs. Now, this is a good strategy for dealing with limited GPU memory where the complex network does not fit into one GPU. But to be honest, there are more efficient ways of using multiple GPUs, such as tensor parallelism that we will discuss, because the chain-like structure, like layer 1 on GPU 1, layer 2 on GPU 2, in model parallelism introduces a bottleneck. Well, in other words, a major disadvantage of model parallelism is that the GPUs have to wait for each other, as you can imagine, right? So they cannot work efficiently in parallel as they depend on one another's input. Coming to data parallelism, it has been the default mode for multi-GPU training for actually several years now, right? So in this approach, we divide a mini batch into smaller micro batches, and each GPU then processes a micro batch separately to compute the loss and loss gradients for the model weights. Now, after the individual devices process the micro batches, the gradients are combined to compute the weight update for the next round, right? So this is a visual representation of that I generated using AI. So an advantage of data parallelism over model parallelism is that the GPUs can run in parallel. Each GPU processes a portion of the training mini batch, that is a micro batch. However, A caveat is, the caveat is that each GPU requires a full copy of the model, and as you can imagine, this is obviously not feasible if we have large models that don't fit into the GPU's VRAM. Then comes tensor parallelism, also known as intra-op parallelism, and it's a more efficient form of model parallelism basically. So here the weight and activation matrices are spread across the devices instead of distributing whole layers across devices, right? So the individual matrices are split. So basically we split an individual matrix multiplication across GPUs. We can implement tensor parallelism using basic principles of linear algebra, right? We split a matrix multiplication, for example, across two GPUs in a row or column-wise fashion, right? If we have two GPUs, just a made-up example, but as you can imagine, this concept can be extended to an arbitrary number of GPUs. Just like model parallelism, this approach allows us to work around memory limitations, but at the same time it also lets us execute operations in parallel, similar to data parallelism. A small weakness though of tensor parallelism is that it can result in high communication overhead between the multiple GPUs across which you essentially split the matrices, or in more technical terminology you can say the across which the matrices are split or sharded, right? So for instance, tensor parallelism requires frequent synchronization of the model parameters across devices, and as you can imagine, that can slow down the overall training process. So in terms of practical recommendations, right? Practical recommendations depend on the context actually, right? So if we train small models that fit onto a single GPU, then data parallelism strategies may be the most efficient, right? Now, performance gains from pipeline parallelism, right, which we kind of touched upon in the beginning, that pipeline parallelism borrows ideas from both the categories, right, of the modeling. Yeah. In fact, let's actually touch upon pipeline parallelism in a little bit more detail, since I mentioned it in the practical recommendation, right? So we can think of pipeline parallelism as a form of model parallelism that tries to minimize the sequential computation bottleneck that we discussed, right? And in that process, it enhances the parallelism between the individual layers sitting on different devices. However, this approach also borrows ideas from data parallelism, like splitting micro batches further into micro batches, right? It's definitely an improvement over model parallelism, but it's not perfect, right? There could be idle bubbles. And another disadvantage is that it may require significant effort to design and implement the pipeline stages and associated communication patterns. Now, coming back to our practical recommendations, like we said, it depends on the context. If it's a small model that will fit onto a single GPU, then data parallelism strategies may be the most efficient, right? Like I was saying before I jumped into pipeline parallelism, was that performance gains from pipeline parallelism may not be as significant as those from other parallelization techniques, such as data parallelism, specifically for small models or in cases where the communication overhead is high. And if models are too large to fit into the memory of a single GPU, we need to explore model or tensor parallelism. Tensor is naturally more efficient. The GPUs can work in parallel since there is no sequential dependency as in model parallelism, right? Actually, modern multi-GPU strategies are typically combination of data parallelism and tensor parallelism. So that brings us to the end of this episode. I will see you guys again on Thursday.